So in previous episodes we saw some examples of differential equations. We had the linear ones, we had the exact ones, and from previous courses you should remember separable differential equations. Now if you studied all those and practiced with them, by now you should have some experience with what the process of solving a differential equation is like, and also what the solutions that you do find look like. And in all the examples that we did, we always had this constant of integration, and that means there is some freedom there. So given a differential equation, if you find the solutions, there's always a kind of degree of freedom, and that raises the question, how much could I require in addition to the differential equation? How much could I require or specify without running into the risk of overspecifying and finding no functions at all that satisfy both the differential equation and my additional requirements? That is kind of really similar to asking a how many question. So you might wonder, if I have a differential equation, how many solutions does it have? Now that how many question is a tricky one. You easily get confused if you start exploring that. But yeah, there is this question of the degree of freedom and how much choice do we have. Now, an answer that has been put forward by mathematics to address that question, one way of doing that, comes in the form of a theorem about initial value problems. And it goes like this: for the first order linear ordinary differential equation, there is the existence and uniqueness theorem about initial value problems. It goes like this: if I have some interval for the independent variable, say variable t, if we would study something that depends on time, variable t. So we have an interval about t on which the differential equation is well behaved. That means that all the coefficients that occur in the differential equation are well behaved. Then on that interval I might pick any point, so any value for t, and at that point I might specify any value that I would, the solution of the differential equation, to take at that point. And then, according to the theorem, there will be exactly one function that satisfies both the differential equation and my extra requirement. One. So it will exist, there will be a solution that is the existence, and there will be exactly one solution that satisfies my extra requirement, and that is the uniqueness.
This animation demonstrates the existence and uniqueness theorem for solutions of a linear, first-order, ordinary differential equation. We focus on the interval on which t takes values between 0 and 1. On this interval, all coefficients of the differential equation are continuous. According to the existence and uniqueness theorem, this is a sufficient condition for a unique solution to exist for initial value problems for the differential equation. That is, within the interval, we may freely choose a value for t, say t0, at which we may freely specify which value we want the function y of t to take. In the animation, this prescribed value is depicted as y0. According to the existence and uniqueness theorem, for each such choice of t0, and then for any choice of y0, there will be exactly one function y of t that satisfies the differential equation everywhere in the interval, and that takes precisely our specified value y0 at t0. This provides some visualization of how much we can choose, indeed, how much we can specify, about the solution of a linear, first-order differential equation, such that the equation still has a solution meeting our extra requirements. And, if we would specify more, then there might no longer be any solution meeting all our requirements.
So that gives a precise statement of how many extra requirements you can put in addition to the differential equation, such that by doing so you pick exactly one solution. So that gives a kind of an answer to the how many question. Once I have selected one value for t, then there are as many solutions for the differential equation as I could specify values for the functions that I want that function to take at that particular value of t.
We may of course also plot the solutions of several initial value problems together, in a single plot. This is done in this animation. The curves shown all are solutions of the linear, first-order, ordinary differential equation shown in the title of the plot. In this animation, we show the solutions on a somewhat wider interval than in the other animations. The solutions satisfy the initial condition that are indicated by the black dots. It is important to note that the solutions do not intersect, although they do approach coinciding asymptotes. But that is not the same as intersection. Indeed, solutions of a first-order, ordinary differential equation cannot intersect. This is a direct consequence of the existence and uniqueness theorem for initial value problems. For this theorem essentially says that through each point in the ty plane shown here, precisely one solution curve will pass.
Furthermore, the theorem says that that solution will exist throughout the interval that we started with. So if the interval is characterized by the fact that on that interval all the coefficients of the differential equation are well behaved and continuous is sufficient, then the solution that you pick by specifying that initial value, as they call it, will exist throughout the interval. And that's called the initial value, the existence and uniqueness theorem for the initial value problems. So, slight note, the initial value is not necessarily specified at the beginning of the interval. It can be any point in the interval. So specifying one initial value, that is picking a time and specifying the value, selects a solution. Second warning, if I pick another value of time and specify a value, that does not necessarily give a new set of solutions, because these these solutions exist throughout the interval, so they exist at any point in the interval, and to pick one I specify the value of a particular solution that I would have in mind at a particular point.
So, beware of the following. Any chosen pair T0, Y0 uniquely selects a solution of the differential equation. Vice versa, any solution of a linear differential equation at a specified value T0 for T takes exactly one value for Y. This is the same as saying that the solutions of linear differential equations are single-valued functions. However, as this animation demonstrates, one single, selected, fixed function, being a solution of the differential equation, may of course satisfy different initial values for different values of T0. That is, it may solve different initial value problems if they differ in their selected values for T0. In other words, different initial value problems for a given differential equation do not necessarily give rise to distinct solutions of the differential equation.
So I think that is how we can appreciate the initial value problem as put forward by mathematics. Actually, I don't think in aerospace engineering, if you would plan a space travel to Mars, I don't think it would be very natural to conceive that as an initial value problem, right? You would have to navigate and correct the trajectory while you go in order to get there. So that's a navigation problem, it's an engineering problem, it's not an initial value problem. But the initial value problem as put forward by mathematics is to be appreciated because it does provide a clean answer to the question that sooner or later you will have. If given a differential equation, you wonder how many solutions does it have? How much can I require to specify in addition to the differential equation such that there will still be a solution of the differential equation satisfying my requirements and without running the risk of over-specifying. So that there will be no longer any function that satisfies the differential equation and the extra specifications.
So here it is. The complete formulation, as in the textbook, of the existence and uniqueness theorem for initial value problems for linear, first-order, ordinary differential equations. It applies to the linear differential equation in the standard form as shown. Note especially that the coefficient of dy dt does not take the value 0, that is, not anywhere in the interval considered. Furthermore, both the coefficient p of y and the function g of t at the right-hand side of the equation here must be continuous on an open interval, say for t lying between alpha and beta, for the theorem to be applicable. If these conditions are satisfied, then, for any value t0 for t, to be chosen within the interval, and for any corresponding choice of the value y0, there will exist exactly one function that will satisfy the differential equation throughout the interval, and that will take precisely the value y0 when t equals t0. A proof of this theorem could be readily based on the method of integrating factors, which we developed in an earlier episode of this course, for linear, first-order, ordinary differential equations. For if we have a robust method that can construct a solution, then the solution must exist. Using the constant of integration, we can always satisfy the initial condition posed. Vice versa, the initial condition unambiguously fixes the value of the constant of integration, and therewith it uniquely identifies the solution. To analyze, and rigorously prove, that this strategy will always be successful, and especially that the conditions on P and G that are mentioned in the theorem are sufficient for this, is an enterprise that belongs to the branch of mathematics known as analysis. We shall not go into these details any further in this course. For comparison, we shall briefly consider the existence and uniqueness theorem for nonlinear differential equations. The general form of these equations is quite general indeed. The right-hand side is a general function, f, of both the independent variable t, and of the dependent variable y. Notice that again the coefficient of dy dt has been normalized to 1. The theorem is applicable if both the function f and its partial derivative with respect to y are continuous. These continuity requirements are to hold on some open, rectangular region in the ty plane. Once more, within this region, an initial value y0 is specified for y, at some value t0, for t. Existence and uniqueness, however, is guaranteed by the theorem only in some interval about t0. This interval extends in both directions over a distance h, for some positive h. Note, however, that the theorem provides no clue about the value of h, nor about how to obtain this value. H may be very small. Moreover, it may depend on the solution for y, which in turn will depend on the initial condition. Indeed, the value of h may depend on the initial condition. One reason for this lies in the mathematical notion of solution that is used here. That is, a solution is supposed to be a mathematical function, while a function y of t is supposed to be single-valued. When we studied exact equations, however, we saw that solutions of such equations come in the form of level curves of scalar fields, and those curves may well curve back, so that they become multi-valued with respect to the independent variable. So, we see that the existence and uniqueness theorem for nonlinear differential equations provides a much weaker statement about solutions than the corresponding theorem for linear equations. In case of nonlinear equations, unique solutions of an initial value problem are only guaranteed to exist locally, in the neighborhood of the initial point.
Now, as regards the existence and uniqueness of solutions of nonlinear differential equations, the situation is rather different from the situation that we had with linear equations. So for linear equations, we had that solutions, once selected on a sound interval, exist throughout the interval. If you study the theorem for existence and uniqueness for nonlinear first-order differential equations, then it's rather more complicated, the phrasing of it. It says there does exist, once I pick a point and specify a value, then given some requirements about the differential equation, there does exist an interval around that point, a region around that point, in which there exists a solution for the differential equation. So that is rather limited. There's no general statement about it that it will exist throughout the region where the differential equation is found. It will exist locally in some region around the point where you specify an initial value. Now that one reason for that is that, as we saw with the exact equation, for exact equations we had these implicit solutions, and they were level curves of function psi that we associated with the stream functions in fluid dynamics, for example. And level curves may curve back. That means there's nothing wrong with the curves, but there are no functions, because the notion of a function in mathematics really is that it takes one value at each point along the horizontal axis. And these level curves can easily be multi-valued, they might even be under like that. So that is a tricky thing, and that is something that may easily happen with nonlinear differential equations. Just a general remark about a way of speaking about differential equations in mathematics. So we talk about linear differential equations and nonlinear differential equations. Now, linear differential equations are very well specified. When we talked about the first order linear ordinary differential equations, we specified very exactly what they look like. And starting from that, we developed a strategy for solving them. So for those equations we have a good theory. So those were linear equations. Now, nonlinear equation is everything else, everything that is not linear. So linear equations is kind of a qualification, and then nonlinear equations is a kind of a non-qualification. So non-linear equations are not specified, except that they are not linear. So there's not much of a specification, and then there's not much of a foundation either to build a theory on about that enormously wide class of equations. So you should lower your expectations as regards a general theory about non-linear differential equations. So that is something to keep in mind.